Hi guys, welcome to a new video of Introduction to Parallel Programming for Noobs. Today we're going to talk about a new method to make an integration. In the previous video we talked about trivial parallelism and show how can we use it to calculate an integration. So we use the rectangle integration, and today we talk about trapezoidal rule. The only difference is the same concept, the same idea, just that this time we are going to use some trapezoids to calculate and not using rectangles. Why? Because we have less error. How? Suppose this is a sum of a function and we are doing some rectangle of a interval of the domain. We see that this error is exceeded, right? So now let's do the same function, the same part of the interval, and instead of doing the rectangle we're going to do a little diagonal. So now we have a trapezoid, right? And we are not considering this portion of area that make us do an error. This is not a strictly demonstration of why it's better to use trapezoidal rule than rectangle, but it's just to get the idea that's better. So now let's see how we are going to use it in a program. Let's see. We have the quarter circle here. Remember, it's from 1 radio, and we saw how we distribute the processors to calculate each rectangle, right? So let's see how can we do this. In definition, the integral in trapezoidal rule will be the this is mess. So this is the definition when we do a trapezoidal integration, and for multiple intervals, multiple trapezoids, we're going to have this form. Remember, b minus a is equal to x, and this will be the following way. Assume we're starting from 0. Okay, it's not have much space there. So let's draw it again just to make it clear. We have x0, x1, x2, blah blah blah. And now our trapezoids, right? And this is tilde x. So if we factorize this sum, we can have the following way. I'm sorry, this is plus minus in. That's confusing. And this is the same that So let's see that in the integral we are just calculating the first and the last function only once, and the rest of the functions twice. Let's consider this to make our code. So let's do it. So this is the code. It's the same that we used the last video. I'm just changing a few lines to use this trapezoidal rule. So let's check. This is the main part of our integration. Again, we are iterating through each interval, right? And again, we are calculating x and y. So this time, if you remember, we are calculating, it must be 2 times for all the values, but not for the first and the last one. So we just add an if clause. If it's different from the first and different for the last one, we do it 2 times, right? And again, just sum pi reduced to the partial sums of pi to a sum pi and multiply it. Be careful with this, we are not multiplying by 4, we're multiplying by 2. Why? Because if you remember, our formula was half of the sum. So we have a half, and 4 we have just 2 times, not 4 times. And we are running again to see the error and the time of this method. So here we are. We're going to compile this code. Again, remember MPICC, we're using the math library just like a normal C program, and the source code. And now we're going to execute it. Remember MPI exec dash end and the number of processors and the program. The in number of intervals we're going to try with 10 millions of intervals. Check with 2 processors. The time is that 1 second, the value of pi. We're going to test with 3 processors to see the difference in time. We see that it's less, not much less, but it's less time. And we're going to try it with 4 processors, and we see that it's also less. But it's between there. There's not much different. If we have that 1 seconds for 2 processors, it's almost half for 4 processors. That's 0.7, no? Almost there. So it's another way to make an integration. And check the error is more precise than the rectangle method we used before. If you don't believe me, let's run the previous method with rectangle. If you remember, it was ejemplo 1. Check the error. I don't know, just check how many zeros. Error 3, 6 zeros for rectangle and 3, 6, 9 zeros for trapezoidal rule. So we have much less error using trapezoidal rule than rectangle. Well, hope you like this video. Subscribe and like, please. And in the next video we're going to see an even much better method to do an integration with less error. Hope you like it. See you soon.